Hi everyone, welcome to our webinar. My name is Rafał Nowak and again I will be your host today. We will be pushing BCIs out of the lab and looking towards real-world BCIs applications. And I'm very happy to welcome our guest speaker. We have today with us Professor Frédéric Dehais. Good to have you, Frédéric, and thank you for joining us.
Thank you. Yeah.
So welcome, Frédéric, and we'll start with the quick introduction of our speaker. So Frédéric Dehais is a full professor at the Higher Institute of Aeronautics and Space at the University of Toulouse. He is also holding the AXA Research Fund Chair in Neuroergonomics and the ANITI Chair in Neuroadaptive Technology. He directs the Neuroergonomics Center leading team of 20 experts in neuroscience, signal processing, computer science, and human factors. His research spans fundamental studies with fMRI to real-world applications using portable brain imaging like EEG and FNIRS. He also co-chairs the International Neuroergonomics Conference. He's co-chief editor of Frontiers in Neuroergonomics, and he co-founded Hinfact, a company developing monitoring technologies for safer operations. So welcome everyone, and welcome Frédéric, over to you.
Yeah, thank you very much, Rafał, for this introduction. I'm very honored to be here to present my research. Yeah, thank you for the introduction. I'm Frédéric Dehais, full professor at ISAE-SUPAERO, so located in southwest of France, Toulouse. And this is our center. Like we are 20 researchers with a multidisciplinary background. And today my talk, I will address two things. The first thing, I would like to define what is neuroergonomics and why is it important. And then on the second part of this talk, I will address the challenges of implementing brain-computer interface in the real world. So let's start with neuroergonomics, and I would like to show you a movie, a real footage from a real accident that I would like to comment and explain how we can address these kind of issues using neuroergonomics methodology. In this accident, you have two pilots, backseater, and the alarm has been yelling for the last 2 minutes, and nobody is responding to the alarm. The alarm is modulated to no response. So in this movie, as I mentioned, you have two pilots plus the backseater, and none of them heard the landing gear warning. They forgot to release the landing gear. So you might say they are not professional pilots. The design of the alarm is not optimal. It's a continuous sound. And you know that at some point, the brain will filter it out. But the common approach to understand this type of events, type of phenomenon, is to adopt a human factors and ergonomics approach. And the idea is to place pilots or participants in realistic settings like flight simulator, and you collect like subjective data. What is your level of workload from 1 to 10, level of fatigue from 1 to 20, whatsoever. You can ask also questions like how many alarms did you miss? You can also collect objective measures like accuracy, reaction time. So I mean, this approach is very interesting because you're placing, obviously, people in realistic settings, but there are some cons, like you're mainly considering subjective data, and it's a brainless approach. And the brain is important when you want to operate an airplane or when you make everyday life decisions. And also, sorry, it doesn't explain this kind of event, but again, it's our raw footage from a real accident that occurred like 4 years ago. And here you have the 3D reconstructions of the landing. So they are about to land on the runway very close to the ocean. And for some reason, they will face bad weather and they will lose visual on the runway.
Approaching minimums.
Sync rate.
First alarm.
Sync rate.
Second one.
Glide slow.
Third one.
Glide slow.
They should go around.
Sync rate. Sync rate. Glide slow. Glide slow.
100.
Glide slow. Glide slow. Sync rate. Sync rate.
And it ended up in a dish landing just very close to the runway. One passenger died and they lost the aircraft. So here we're dealing with professional pilots. We cannot blame the design of the auditory warning. So yeah, maybe we should consider neuroscience to better understanding what's happening in the pilot's brain And we have these cool tools like fMRI, MEG, electroencephalography. And now we have a good understanding in what's happening in the brain when you process both visual and auditory information. These are the neural networks that are involved when you process like this type of sound while doing a visual task, okay? But the thing is, we got an accurate measure of the brain using these tools, but the participant freedom of movement is like super constrained. And we're restricted to some kind of simple and protocol and simple stimuli. And I really like this sentence from one of our, unknown, very brave participants stating, "Why are your experiments so boring? It is like torture. All you are recording in your experiments is brain activity involved with being bored to death versus sleeping." And as a neuroscientist, it means a lot to me, because are we really measuring the brain when we place participant for 2 hours in an fMRI, for instance? So this led Professor Parasuraman to propose to merge this mindless neuroscience together with this brainless human factors ergonomics approach into what he called neuroergonomics. And neuroergonomics is defined as the measure of the brain at work and in everyday life. And why can we do neuroergonomics research nowadays? Because we have now very portable, very mobile devices like portable eye tracking, like this nice EEG system from Neuroelectrics, for instance. But also we can use like in-ear EEG, where we could place electrodes inside the ear or around the ear. And we can, at some point, decode brain response, and we can record brain activity outside the lab, which is very interesting. But still, from a methodological point of view, what we propose, together with my colleague, Dr. Hassan Ayaz, is to start anywhere from collecting data using traditional neuroimaging techniques like fMRI, and then progressively go into the field, like more realistic settings in the lab or in flight simulator, and outside the lab, like measuring the brain when you walk, when you operate a real aircraft. And it's when you combine all these measures collected in these different environments that you can get a good understanding of what's happening in the pilot's brain. And I would like to illustrate this methodology with the first experiment we conducted some time ago using fMRI to investigate this inattentional deafness phenomenon to auditory alarms. So we did this study with Dr. Kalan, who works in Japan at ATR, and then we place like Japanese pilots in the fMRI. So the head is in the fMRI, and the hand is outside of the MRI, and they can, operate the joystick. And pilots, they have to do this crazy reduction, the Red Bull race. They have to pass through the gate. Okay. So it's quite challenging. And at the end, along with the flying task, they have to report auditory alarms by pressing the trigger. In this experiment, our pilots missed 35% of auditory alarms. So at some point, it was a good news for us because we have image of the brain when the pilots were responding to the alarm, and image of the brain when the pilots were failing to respond to the alarm. So then you just compare this the activations, and that what we get out of it, we saw that. So this is the back of the head, frontal part of the brain. And we saw that when pilots were missing the alarm, we had this frontal brain activation, like inferior frontal gyrus and pre-SMA, okay, that were activated when pilots were missing the alarms. And we know from the literature that these brain regions are related to the activation of a so-called attentional bottleneck that will promote selective attention. It's like when you drive, let's say, around Barcelona, the city is beautiful, the scenery is beautiful, and you have time, you can look at the sea, the mountain, and so on, and all of a sudden someone is crossing the streets, then you can only focus on, trying to dodge and to avoid the accident. So that's what this attentional bottleneck is about. But then we did some more advanced analysis, namely connectivity analysis, because the brain is not just about brain regions, but it's more about kind of a network, a hub, I would say. And we look at what are the consequences of the onset of this attentional bottleneck on the rest of the brain. And what we found out is that when this attentional bottleneck was activated, in return, it shut down this brain region. So blue means deactivated, and this brain region is the auditory cortex, okay? So you face a stressing situation, you have this activation button, the attentional bottleneck that is activated, and in return, it shut down your hearing. Okay, so in a nutshell, when you face something very stressing, very unexpected, then you shut down the hearing, and you're unable to process any kind of auditory signals or auditory alarms. So fMRI is very interesting because it has a nice spatial accuracy, but the temporal accuracy of fMRI is not that good. So we did another study in our flight simulator using EEG, electroencephalography. So we place our our participants in the flight simulator. I don't know if you can see, but there's smoke in the cabin, so it has to simulate like fire in the cabin. They have 20 minutes to land the plane. The landing is very critical, and you see that this is the 3-axis simulator is moving in all directions. The participant is wearing a mask and so on. And along with the flying task, participants were required to respond to auditory alarms. So the scenario was so realistic, so stressing, that our pilots miss 57% of auditory alarms. Okay, so I don't know how familiar you are with electroencephalography, but I will try to explain. So here, this is time 0. Okay, and on the x-axis, we have time in milliseconds. So what you can see in blue, this is the temporal brain response when pilots perceive an alarm. So this is the brain response in blue when they respond to an alarm. And in red, this is the brain response, or should I say the absence of brain responses when the participants fail to hear the alarm. And what you can get out of here is that the red curve is like kind of damped, attenuated. And one important thing, if I clap my hands, first you will hear it in the auditory cortex. This is the perceptual stage, but you probably weren't able to say, oh, who did that? Where does it come from? What does it mean? It takes like 300, 400 milliseconds that awareness arises, that you are aware that I clapped my hands. And what we get from this graph is that already at the perceptual stage, there's attenuation of the processing at the early stage. What I mean by that is that these mechanisms, these inattentional deafness mechanisms, is an early and unconscious gating mechanism. It takes place in 100 milliseconds before awareness. So in a nutshell, it's not you who decide to shut down the hearing, it's your brain that decided for you. And let me tell you a personal story. Like back in the days, I loved football. I love soccer and so on. Now I'm cured, I don't love football anymore, but that's a different story. So anyway, I was driving on the ring road in Toulouse, southwest of France. People are driving like crazy in my city. And I was listening to the radio because I wanted to figure out whether my football team has won the match or not. So I was really listening to the radio. And all of a sudden, there was like a massive accident. So I managed to dodge. Nobody was harmed. But at the end, I didn't know whether my football team won the match or not. So, I mean, it makes a lot of sense. And thanks to my brain, I was focused on, avoiding collisions. But in real life scenario, it could be like operating aircraft. It could be very dangerous, like to shutting down the hearing at some point. And on the top of that, what we did is we wanted to see whether we could implement kind of neuroadaptive technology. Like, can we detect at the single trial level, like there's an alarm, there is the associated brain response. Could we predict whether the pilot respond to this alarm or not? Okay, so we train a classifier. If you have any questions, like later on, we can delve into it. But we use like classical BCI pipeline. And then we managed to detect with 70% of accuracy whether the pilot is going to respond to the alarm or not. So at some point also it could allow us to maybe implement neuroadaptive cockpit or smart cockpit that will adapt to the pilot's state, like triggering a visual alarm instead of auditory alarm, tactile alarms, and so on. So, and the last experiment we did were done in our real aircraft. And in the previous experiment, we used gel-based electrode system. And if you want to push neurotechnology out of the lab, you may want to consider dry EEG system, okay? Because like you pilots or you yourself would never accept to wear like this gel, which is sticky and fishy at some point. And you want to use dry EEG system. And with the dry EEG system, we know that the signal to noise ratio is not as good as a gel base, but still we want to test whether we could measure this phenomenon in the real world using dry EEG system. And that's what we did. So in my university, we are lucky enough to operate a real aircraft. And I'm the backseater, I'm the one recording brain data. This is the participants. And this is the flight safety pilot. Okay. Here you can see we are measuring like on the fly brain data. And when the pilot pay attention to an alarm, then he has to respond by pressing the button. So here, this is the real world. And you see this is a real landing with crosswind. So the landing is quite challenging. And this is exactly what we want to measure, like the brain facing real stressing situation. And usually this is during the landing that pilots start to miss these auditory alarms. And as you can see here, we were able to replicate the findings in the flight simulator, like with attenuation at early stage and no awareness when pilots fail to hear the auditory alarms. But the main topic of this experiment was to look at the brain like 3 seconds before an alarm, with the idea of can we predict whether the pilot's brain will be able to respond to a future alarm? Like, let's say that in 3 seconds there will be an alarm. Will my pilots will be able to respond to it? So we did a little bit of source localization. I won't trust this result that much because this is only 32 EEG system in the real world, but still 3 seconds before a missed alarm, we saw the activation of the attentional bottleneck, like we found in the fMRI. So at some point, we get some consistent results with the fMRI. And then on the top of that, we did some classification using data 3 seconds before an alarm, and we almost 70% of accuracy, we could predict whether the pilot will respond to an alarm. So in a way, we could still implement more proactive cockpit that will adapt to the user in advance. Like no need to trigger any auditory alarms, just need to trigger another signal, for instance. But the thing is, in this experiment, we use a 32 EEG system, and it's a bit cumbersome. Like, I mean, for science, it's okay, but if you want to implement it in a real cockpit or in a car, you don't want all these electrodes. You want less electrodes. So we did another study using still the Inobio system, but with the idea of using only 6 electrodes. And we targeted these electrodes because we know that they explain, I mean, they are the good one when you want to investigate auditory attention. So in this experiment, we manipulated workload, and participants, they have to do two traffic patterns, like taking off and landing. In one scenario, it was the low load condition. They were not flying the aircraft. They were just supervising the flight instructor flying the aircraft, okay, low load condition. And in the high load condition, the participants, they had to actually fly the aircraft. And along with the flying task, low load, high load, they have to pay attention. They had to perform this auditory oddball task. And this auditory oddball task is quite classical in psychology. It is like you have 2 types of sound, like beep, 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 like high pitch, for instance, and you need to count the deviant sound. How many? So low load condition, auditory oddball task, high load condition, auditory oddball task. And still, this is quite consistent with what I explained earlier. When you have a rare sound, like this high pitch sound, for instance, it gives rise to a nice, what we call P300 brain response here. And for the frequent sound, you have no brain response because there's some kind of habituation. So what you expect is that for the rare sound, you have this nice P300 response, and in black, no response when you ignore the frequent sound. We can also use the P300 amplitude as a marker of mental workload. What I mean by that is that when the pilots, they only have to pay attention to the sound, they're not flying, they have a lot of cognitive resources to process the sound. So you expect a nice P300, like nice P3 like this. And when you fly and you, along with the flying task, you have to respond to alarm, you don't have that much of cognitive resources. So you probably miss a lot of alarms and you expect no P300s, no awareness at some point. Okay? Just to give you an idea of how it looks like. So just in this spec, it's another experiment where we use 32, but trust me, in this experiment, we use a 6 dry EEG system. It looks like this. This is the rare sound. The one you have to count. This is the frequent sound. You ignore this one. Ignore this one. Ignore this one. And ignore it. And you have to count. So it's 2. You have 2 infrequent sound. That's what you're supposed to do with the flying. It looks easy, but it's not that easy when you fly an aircraft. So the thing is, when you are using only 6 electrodes, you cannot use any fancy advanced signal processing techniques like independent component analysis. And if you just filter your data, this is what you get, like super noisy data. There's no P300, no brain response that you get from this. So we use the artifact space reconstruction techniques, which is named ASR. We use the Riemannian version of ASR. And it's really good at removing short time, high amplitude artifacts, like eye movement, for instance. I'm going to show you here. So in blue, you see like, for instance, it should be like eye movement, I would say. Oh, no, it's not, maybe kind of noise. And in red, the reconstructed signal. So it's PCA-based, principal component analysis based, and you can run it on the fly. So you see real on-the-fly data. Blue, you can see the artifact, and in red, the corrected signal. And it really does a good job because it removes the noise, but still it can retain like brain signal. And just by using ASR, you see like now, I mean, I've seen better ERP in my life, but we're using dry system, 5 electrodes, 6 electrodes, real world. And you see that when people are paying attention to the rare sound, we have this nice P300 response and no response for the frequent sound. And this is for the high load condition. You see, we don't have any P300. It makes sense because pilots, they don't have enough resources to process the sound. And again, we did some classification, workload classification, and we managed to get like 71% of accuracy. Okay, so this work is just to show you that neuroergonomics methodology, neuroergonomics research is quite interesting and promising. But in this experiment, we did like mostly offline analysis. And I would like to see that we can really now go for online implementation of BCI that we can use for both clinical and especially aviation application. So there's 2 types of brain-computer interface. You have active BCI. So the idea is that you're using your brainwave to interact with the system, like to promote hands-free interaction. Just think about left hand, right hand, and then you can turn left or right. And then passive BCI is a different framework. This is what we did, that what I presented so far. Now you want to monitor the brain states, like the level of stress, the level of fatigue, so that you can adapt the interaction accordingly. Now let's say you detect pilot's overload, then you may want to trigger the autoflight system to lower the workload. So first, we're going to talk about active BCI. And I would like to explain the technique that is a classical technique that is very popular in the BCI brain-computer interface community. And it's quite simple. It's called steady-state visual evoked potential. And the idea is pretty simple. You just have to flash, let's say, LED or a flicker, let's say at 12 Hertz, okay, like 12 Hertz flashes. And then it turns on and off at 12 Hertz. And on the back of the head, because you have the visual cortex here, you can get a kind of brain entrainment of the visual cortex. So you can measure 12 Hertz on the back of the head. So if, let's say, the participant is looking here, focusing here, you can measure 11 Hertz here. So you can decode at some point where the participant is focusing on. So it works pretty well. It has a nice signal-to-noise ratio. And in less than 1 second, you can decode participant attention. Let me show you some examples done by some colleagues. Here it's a speller. So you see that all these letters and digits, they are flashing at a different frequency, or maybe same frequency, but a different phase. And the participant now is focusing on the E. It taps E, on A. So you see it's hands-free, it works pretty well. But still, there's a lot of drawbacks with these techniques. The first one is that you need to calibrate the BCI. Like each time you use the BCI, you need to calibrate it. For example, some Chinese colleagues implemented a 160 key keyboard, but it takes 40 minutes to calibrate the BCI. Okay, because we need to train a machine learning algorithm to decode, to learn your brain response to 11 Hertz, 12 Hertz, 13 Hertz, 40 Hertz. So the more classes you have, the longer it takes. And no one wants to calibrate the BCI like for 40 minutes. Like for every day, you have to recalibrate it. And also, the thing is, it's not really self-paced. The user needs to adapt to the flashes. Okay, the interaction is paced by the machine, not by the human. And also something that you don't see in these videos is that if people do not look at the screen, it will type random letters. Why? The reason is that because the BCI didn't learn a no class. They didn't learn what is a no letter, what is an absence of, what is the brain response to no flashes. So it has some issue. Something that you probably didn't see is that these flashes, like this is a 4 class, they are using moving up, down, left, right character with these flashes. It's really straining on the eye. Okay, let me show you again. It really hurts the eye. So it induces visual fatigue. It could lead to headaches, and worst case scenario, it can trigger epileptic seizures. And when you want to use these devices in realistic settings, it's quite slow. It doesn't work that well, I would say. It works well when you don't move. You're like facing a PC and so on. Okay. And also in most of these studies, they're using wet EEG system. So what I'm going to show is that our recent research is dedicated to design what we call the invisible BCI. By invisible BCI, we mean like transparent flashes and also like a transparent calibration that lasts less than 1 minute. So let's start with the invisible flickers. So flickers, how does it work? It goes from, white to black. This is full contrast. And it really hurts the eyes. It's really painful. So we came with the idea, can we play with amplitude depth reduction? Can we go like, white to gray? So it's becoming more comfortable and like even more comfortable to an extent that it is, barely visible. And as a proof of concept, we did the first experiment, very basic, very simple. You have to fixate, you have to look at the fixation cross for 3 seconds. And on the left and right part of the screen, you have flickers, 13 Hertz, 15 Hertz. Then for 3 seconds, you have a cue telling you that the target will appear left or right. Okay, 3 second fixation cross, 3 second cue, and 3 second the target, and you have to respond left or right. As simple as that. So we had 3 conditions. This is the control condition, where you have this, very straining on the eye flickers, and you see you have the cue, you have the target, and you have to press right. And then we implemented a staircase procedure. We started flashing from 0 to full amplitude, and we asked the participants, say when you start to see the screen flickering. So you have to define a subliminal threshold. It's flickering, but you don't see, and a periluminal threshold. It starts boiling, it starts flashing, but barely you cannot see it. So let's go for subliminal. You have the flashes, but you don't see them. The task is going on, the cue, here. And let's go for the periluminal. Maybe you will see the edges flickering. The edges are flickering at some point, but you barely don't see them. And the research question is, the research question is, can we still measure the brain response? And the response is yes. So this is the control condition when you have like almost full amplitude flashes. So fixation cross, you have no brain response. Then you have a cue, left or right. So you see that the participants start to engage and the participants respond and then disengage. Okay. And what is nice is with the periluminal and subliminal, we still can decode this like fixation, engagement, disengagement, still with attenuated response, but we can decode it. And the next step was to see whether we could do like single trial classification to predict whether the participant was attending the left part, 13 Hertz, or the right part, 15 Hertz. We didn't implement fancy algorithm. It was like pretty straightforward. But in the control condition, it was very easy to decode whether the participants were attending left or right. In the periluminal condition, you barely couldn't see the flashes, and still we could decode left, right attention. And the subliminal condition, you couldn't, it was chance level. So in a nutshell, what we recommend if you want to do like purely, I would say, basic, fundamental neuroscience research, you can go with subliminal, because when you average all your trials, you get a brain response. If you want to do like real-time classification using almost invisible flickers, you should go with periliminal. So you probably don't see the point of using this these transparent flashes, but we wanted to see whether we could use it to tag vigilance, fluctuation of attention. And we use for that the quite famous Mackworth clock paradigm. It's a very, very boring task. Never do this task if you're invited to. So you have a dot that goes from one position to another. And from time to time, it's keep a position. And then you have to press the space bar. And this task lasts forever. It's very boring. Usually after 20 minutes, you start having a lot of misses. So what we did, we place an elusive flicker on the top of the task with the idea of when the participant is engaged, has a good performance, we could decode like 14 Hertz on the back of the head with a strong signal. And when the participants disengage, maybe experience mind wandering or whatsoever, the brain response will be attenuated. So to do that, we implemented a flicker on top application that is available on GitHub. So you'll see, like, implementing flickers is very tricky because you need to deal with the frequency rates, refresh rate on the screen. If you want to have multiple flickers at the same time, it could be difficult, as challenging in terms of computational power. So we implemented this app. You just have to drag and drop some flickers. You can play with the transparency. Just an example. It could be more or less transparent. Up to 40 flickers. And you can choose your textures, and also you stream your data on LSL. So you know at any time where is your flicker, where it flashes. And you can put an overlay on any application. It could be like on Word, like placing this kind of tags on any application. So I mean, this is what we did. We placed this flicker here. And let's take a look at the results. So we had 16 participants. These are the results for, let's say, 4 participants, but it's consistent with all our volunteers. So in blue, you have the signal-to-noise ratio measure on the back of the head. And what is nice is you see that you can really capture fluctuation of attention. It's not possible to be like fully engaged, like you're listening to me for the last 40, 30, 35 minutes. You're not always fully attending my talk. So you experience fluctuation of attention. Okay, you see that. And in the dotted line is the mean of the signal-to-noise ratio. And what is nice, it stands true for all our participants. So red cross is an attentional lapses, meaning that the participant failed to press the space bar, failed to not the jump. And then when we have a true, when it is very low, the signal-to-noise ratio is very low, we have an attentional lapses. So it looks like this measure is very predictive of attentional lapses. And you see here, like before 1 second, and we can look at 1 second before a lapses. When there's a hit, there's a strong brain response. When there's a miss, there's a very weak brain response. And if you look at alpha oscillation, which is known as good markers of attentional lapses, there are absolutely no differences. And we did a bit of source localization. And when you can see, like, we can go back in time. This is the participant supposed to press the space bar. In green, it's a hit. And when you have a miss, you see, like, we can go up to 15 seconds, and we can predict whether the participant is going to miss or not the target. Okay. So in this case, we're using like only flickers, transparent, and SSVP. And I'd like to move to the last part of my very last part of my talk. And this is the Starburst BCI that we implemented using the Inobio system. And as I told you, if you use dry AG system, the transparent flashes, you don't get good signal at the back of the head. So you need to improve the design of your stimuli. So based on existing studies and work by previous colleagues, we incorporated like these textures, Gabor-based patches or Ricoeur-based patches that are known to elicit strong response, a strong foveal response. We also use randomly oriented patches, so to maximize the brain response of the visual cortex. So by doing this, we were expecting to have like strong brain response that we could decode with a dry EEG system. And the other thing, if you have questions I could answer later on, we use, instead of using periodic stimulation like 11 Hertz, 12 Hertz, 13 Hertz, we use aperiodic stimulation, space aperiodic stimulation. And the idea is like, if you have brief flashes, you know that it will elicit a strong response on the back of the head. Okay? So when you have a flash, puff, you have a strong brain response, like a kind of impulse response. And why are we doing this? Because at some point, we reduce the classification problem to a two-class problem. Think about Morse code, like beep, 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 things like this. For a human operator, you just need to learn short bursts, long bursts, then you can make letters, words, sentences, paragraph, and so on. Okay? The same thing here. Each letters or each digit has a specific code, beep, 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 beep. We just need to decode response to beep and absence of response when there's no flashes, and then you're good, and then you're good. So at the end, we can go with 40-second calibration. So to implement this BCI, we use this A-dry inhibitor system, mostly occipital, parieto-occipital. We use the time flux environment. It's an open source Python-based framework to implement BCI. I highly recommend this framework. And just to give you, to show you, to illustrate you the BCI, so we're using the dry EEG system. This is the calibration. We're just flashing random flashes just to learn 0 and 1. So it looks like this. And you can see that if you get closer to your screen, maybe you can see the textures, but it's almost invisible. Okay, we're just flashing 0 and 1 just to learn the brain response to this 0 and 1. We're done with the calibration, and now we're going to do the pin pad task. So the participant is supposed to type 6652, 6, 6, 5, and you don't see the flashes. 5, 2. Okay, let's go for another sequence. You should get, if you don't see the flashes, you should get closer to your screen. Six. And what I want to showcase right now is the gating things. Remember what I told you is that when people are not looking at the screen, the BCI makes decision, like erroneous decision, because it's based on correlation. So even if you have very, very low correlation, it will still take the first prediction with the highest correlation. And here, like Jules, my PhD student, is not looking at the screen, and we have a gating mechanism. It doesn't fire. Okay, we have no false positive, almost no false positive, I would say. So we can go mobile. So here I'm going to type 1, 2, 3, 4, 5. It's going to be blue when I'm typing, mentally typing 1, 2. And it's implemented on the tablet, and I will walk. So I'm doing 1, 2, still using this headset, 3. So you have a lot of artifacts. I'm going to walk here and be still able to operate the BCI. Walking again, and I can operate the BCI. Okay? And the last example, one of the last examples I would like to do, here is the 2 task. So the 2 is highlighted in blue. It means that I have to type the 2. I'm doing 2. 2 again, I have to type 2, so it's green when it makes a correct prediction. 5. What is nice here is I'm in a real aircraft. You have no ideas how noisy this environment itself. You know, you have the propeller, you have a lot of electromagnetic information, and still we can operate the BCI out of the lab. And what I want to show you to conclude is that we can use this framework, these flashes, for passive BCI purpose as well. We know that the brain response to these flashes is modulated by attention. Like we did we use this task that is used for pilot selection, or we have, here's our flight simulator, and we place like transparent flickers on the top of this user interface. You might say, why not using an eye tracker? I think, okay, you can use an eye tracker, but the eye tracker does not tell you how much you process the information. It's not because I'm looking at the screen that I'm actually paying attention to the screen. But with these flickers, I can at some point decode how much attention you paid anticipate you all this information. So what you can hear, like the participant is doing the task, you can't see the flashes, because when you use wet EEG, you can use fully transparent flashes. And here on the left, we predict how much attention the pilot is paying to all these different user interface. And with the same in the real aircraft, you don't see the flashes, and we put these transparent flashes here. And on the fly, in real time, you can detect how much attention, how deep the pilot is processing information. Okay. And so we mentioned at the end, so we started some collaboration with in the clinical domain. And you probably heard about these patients that face like comatose patients. So first they're in coma states, then they could evolve into vegetative states, and then like to kind of cognitive motor dissociation. So what does this mean? This means that when these participants, you talk to them, they have no behavioral responses. But for some of them, their brain is still aware. They can hear you, they can hear their family talking to them, they can hear the doctors, but they're unable to show any evidence of behavioral responses. So what we started to do with Professor Steve Einstein at Hôpital Purpan de Toulouse, to use these flashes, so we can embed these flashes into faces, family faces, words, and so on, and flash the participant's brain and see whether we could decode they are responding in the visual cortex, or when they do like a more complex task using connectivity metrics, try to detect whether they're really processing the information and to what extent. So I would like to thank my team who was very helpful to run all these experiments. And if you have any questions, I'll be very pleased to take them.
Thank you very much, Frédéric. So actually, this is actually nice connection, because the previous webinars we have had regarding consciousness and patients in even locked-in syndromes with Aurora Tibau from Coma Science Group. And actually, this was more related to brain stimulation in this kind of patients, but also she was mentioning the importance of, for example, of BCI applications and the way that they can communicate, and how we can actually solve, especially in locked-in patients, that only BCI active or actually passive could be translated into the words. I have like a general questions regarding the first part, regarding the neuroergonomics. So when we are mentioning different ways at the cognitive level of measuring the attention workload, and you are showing different actually cognitive responses, starting with the very early N1, then P3, also mismatch negativity in the middle. Which one do you think would be actually, or would be the most appropriate for the real scenario and real world applications? Because we are showing difference in like in oddball paradigm, we have P3, then we have some difference already on the N100 already in the early stage. There were also, if you could calculate mismatch negativity, there would be.
Yeah. So the thing is, I mean, it's a good question. I'm not sure I will be able to respond to it, because in our classification, I mean, if you look at the statistical level, usually it's the P3, which is the best indicator, the P300. When we do the single trial classification, we are using like covariance matrix. I mean, we are using like a 600 milliseconds epoch. So we are mixing N1, P3 all together. So we didn't look at specifically the N1 will be more predictive than the P3. So I don't know how to address the question. Usually what works better, I didn't explain in the when we did these experiments with only 6 electrodes in the real world. We also use brain oscillations like alpha, theta, and so on. So alpha, theta, these brain oscillations are more robust to artifacts when you're in the real world, and they are more predictive than the ERP. That's what we've shown in the paper. So if you want to do like on the fly detection of mental workload, I would go for these oscillations.
And in terms, actually, I was surprised of having this EEGs, ERPs in the real world, and these are real world in the plane. You were explaining a little bit how you are dealing with artifacts, that you are actually using some specific algorithm to remove the artifacts.
ASR.
Yeah, but the question is actually, how you can trust if you are not removing the important part of the signal, and you are actually dealing with artifacts, and what would be actually the best scenario in the plane, and what would we recommend actually for the manufacturer like we are regarding EEG devices to avoid the external artifacts?
I mean, I would I mean, the thing is why we did this auditory oddball task in the real world. In fact, it was really to test the ASR, the ability to remove artifact and to keep at some point brain signals. And since we have this, you know, you have, when you do the auditory oddball task, you expect N1P3. And without the ASR, we don't have any N1P3. When you use the ASR, you get this N1P3. So to me, it's kind of, you know, evidence that we are actually measuring the brain. And this is typical paradigm approaches that are using by several people when they're doing like skateboarding, like walking, hiking, and so on. So, I mean, ASR, I mean, there's been tested with several other EEG manufacturers who are pushing mobile EEG like you are doing it with Neuroelectrics, are using this ASR and offer this ASR implemented. The only, I mean, there's some controversy about the ASR because people are claiming we are removing things. Don't use it if you're in lab settings, but if you're outside the lab, I would definitely recommend to use it. Definitively.
Okay. Thank you very much. Like regarding BCI, so would you say that the prediction would be that the paradigm that you will use, it will move into the type of stimuli that you were presenting with the star bars BCI, not like typical flashes, because of the visual fatigue. This is the main like downside of the classical P3 speller with the visual stimulation.
Yeah, there's two things. There is you induce visual fatigue, and you can trigger epileptic seizures. So it could be a big issue with patients. And the thing is also you have peripheral distractions. Like when you look to a specific letter, you see the flashes. So it's distracting. And if you're a patient, like especially I have some colleagues in Vienna working with the ALS patients, and they have difficulties operating this speller because they are distracted by the flashes, surrounding flashes. And also it contaminates your brain signal because in your brain signal, you have like the neighboring frequency contaminating your response. So these stimuli, they are designed. So it's based on previous studies from other people that are designed in a way that, I don't know if you take a look at it, it's based on Gabor patches, and it's just kind of small contrast. And the eye and the fovea is very good at detecting contrast. The eye is just an edge detector. So we're giving edge detection task to the eye. So the eye at some point is super happy. And using with this random orientation, you know that we have specific neurons in the visual cortex responding to this orientation, this orientation, this orientation. And you can get very, very nice, like big ERP that even if you're in an airplane or if you move, can still detect them.
Thank you very much. Yeah, but I was connecting, actually, we have been hosting here the group from Valladolid, from Medusa, CVEPS, also going to this code modulated visual evoked potentials. And you are applying a little bit different strategy to the BCIs and especially the passive BCIs. We have a question from Song Lan, and is asking regarding what is the delay between the moment the pilot ignores an alarm and the moment the BCI reports the ignorance.
As I explained, we use offline analysis. I mean, we didn't do that in real time, but still we were using like 600 millisecond epoch. So you have the alarm, and we feed the classification algorithm with 600 millisecond epoch. So at some point we predictive because the motor response, it takes 1 to 1.5 seconds to report the alarm, and in our case it's offline, but still we try to emulate online. It takes only 600 milliseconds to detect whether the pilot is going to respond or not. So it could be very fast. And the second example, we are looking like 3 seconds with sliding windows, 3 seconds sliding windows, like before an alarm. So we could predict 3 seconds in advance whether the pilot will respond or not to the alarm. This is a real prediction in this case. This
is really, really fast. And then we are moving very close to the real world applications. We have also a question from Youssef. That great, you use 6 electrodes. Please, which algorithms you use as feature extraction and classification? Is the operation in real time, all the steps, or use offline for training and testing then in the real time?
So again, for this experiment, what we're doing is like spatial filtering using CSP. So first we epoch the data, we compute the ERP, and we compute the we extract with the power spectrum density to extract the alpha, theta, things, etc. Power spectral density, and then we use this this spatial filtering CSP techniques, and then it's a shrinkage LDA. Very, very simple task, because we wanted to do that. It's offline, but we want to make something that works in real time.
Okay, thank you very much. Next question is regarding practical applications, regarding dry electrodes that can be sometimes uncomfortable and generating some pressure on the skin. So what is your experiences with the over-the-air e.g. that you were presenting at the beginning, if this could be used also for BCI applications, and especially that those are not covering actually the whole cortex, so you will have also only recording from the temporal regions, I guess.
Yeah. So for the Starburst BCI, with these 6 electrodes on the back of the head, I did some experiments for 2 hours, 2 hours and a half to investigate fatigue, and you don't have the feeling that you have this dry EEG system. You don't worry. I'm not going to lie to you. When we're using the 32 EEG system in the real world, you're flying the airplane, you have sun, you also wear other equipment like headset. After 1 hour, it's quite painful at some point, but this is extreme. And something we did, I didn't mention, is that people at Neuroelectrics and other companies that are using this solid gel thing, which are kind of silicone soft. We try using only the solid gel itself. We didn't get good signal, but we came with the idea of like using the dry electrode and plug the. I don't know if maybe I did a crime, Raphael. If it's the case, I really apologize. But
we haven't seen anything.
And with doing this, we were able to get like some. We did this. This sealed experiments in the simulator with these settings, and this was absolutely comfortable. You don't feel having the wearing an EEG system, and at the end you get some kind of nice ERP. So it could be one solution.
Perfect. So another question from the same attendee regarding comparing with like just some eye tracking systems. If you compare the BCI, I guess that those are the applications will be different. But compare with eye tracking, what would be the?
That's a very good one. So the eye tracking is faster than the BCI, and the calibration is like, in some cases you don't need to calibrate it. So I think what I didn't explain in the last experiment with the passive BCI, we are combining EEG and eye tracking. And the thing is, with the eye tracking, for instance, you cannot measure like peripheral vision. And with this, we showed, and some other colleagues showed that before us, that if there's a flash on your left, but you don't look at it, and you're supposed to focus, so to pay attention on the peripheral task, we can decode it with the EEG. You cannot decode it with eye tracking. So that's the first thing. And also the one drawback of eye tracking is that's not because I'm looking actually to Raphael, that I'm actually thinking, or I'm actually looking at him, and and with EEG you can do that, especially with his codes, because the intensity of the response will be modulated to how much attention I pay on Raphael. And so I think combining the two is very interesting. Like you have a fixation and you get the brain response evoked by the codes BP.
I would add also, when you were actually explaining the last clinical cases, when we talked about very important application like locked-in patients, where probably a track wouldn't work at all, and then the only BCI based on EEG could help. So there are different applications for different solutions. And a question from Ellie, actually, what would be the maximum typing speed that you can expect from like word per minute or letter per minute?
Yeah, I think I think it's like 30 characters per minute, I would say. The thing is, there's the ongoing fight with a lot of colleagues trying to get the big ITR, and they go super fast. You have to be super trained, and it's very difficult to do it if you're not well trained. So, and to me, again, the point, I don't see any features in reactive BCI for healthy or even for patients. The future to me is more using BCI for diagnosis purpose. Okay, because for healthy participants, you need to wear an EEG, and in everyday life operation, when you drive your car, when you're at work, when you're with your wife or your kids, I don't see the point. Use an eye tracker or maybe use your hands, and the hands have been designed for. But for clinical application, I think patients will be happy to wear these EEG devices, and it could be very helpful to to diagnose different brain impairment and so on.
Okay, and we are moving a little bit actually to consumer application. There is a question from Ellie. You have mentioned that alpha power is less predictive of user focus compared to steady state visual evoked potentials. How do you think we could implement SSVIPs in consumer real world technologies with the devices like Neuroadaptive Muse for direct consumer use?
Yeah, I think for the Muse you can be limited because you are mostly measuring temporal and frontal things. So what we're doing here in the lab, we're trying to, we're using your system or other system, like try to minimize the number of electrodes then you can put on the back of the head. What I demonstrated is that you can implement these flashes on a laptop or on a phone, on the mobile things. So I think there's a future, but you need to have the to target occipital, parieto-occipital region if you want to use it. But
Okay.
you just need like 6 electrodes, maybe less.
Perfect. So last question, actually, this is regarding the real world applications. The ERPs need fixed events so that you can calculate the windows for your classification. Have you tried classifying true passively in the background without the event info, like a moving window?
The response is yes. We have a recent paper, something done with my colleague Simon Ladouce. You may want to take a look at it. We use like sliding windows, and we learn a response. We learn the prototypical N1P3 response, and we slide it because it was a free exploration. People have to find books in a library, like good books, ignore them. So we have no cues. We use the eye tracker, but it was not that useful. So we learn a response, and using sliding windows, we were able to find ERP in the real world.
Okay, perfect. Thank you very much. So this was our last question. Thanks, Frédéric, for the presentation. Thank you very much for the questions, for answers. Thank everybody for joining us today. And I hope you're gonna join us for the next webinars. You can visit our webpage, neurolexic.com, where you'll find more information. So thank you again, and have a great day. Thank you, Frédéric.
Bye-bye. Thank you.
Thank you very much. Thank you. Goodbye.